Calculus AB review. We look at function analysis using derivatives, aka how to use the first derivative test and concavity in order to classify increasing, decreasing intervals, local extrema, so on and so forth. So let's get to it. So increasing, decreasing functions in the first derivative test. Recall that the first derivative can be used to determine if a function is increasing or decreasing. If at a point x equals a, the derivative is greater than 0, the rate of change at a is positive, so f is increasing, while if the derivative is negative, the rate of change at a is negative, so f is decreasing. Critical points, points at which f prime of a equals 0 or is non-existent. The first derivative test is that we locate the critical points and then we evaluate the derivative in between the critical points. We use this to classify local extrema and increasing/decreasing intervals. Concavity. The second derivative measures the slope of the tangent line to the graph of f prime at some point x equals a. So for concavity, if we are concave up, the graph of the second derivative, the graph of f, opens upwards, which means that our second derivative at the point is greater than 0. Concave down, the graph of f opens downwards at a point, which means our second derivative at x equals a is less than 0. Inflection points, points at which a graph of f changes concavity. Either the second derivative equals 0 or does not exist, and changes signs near x equals a. Second derivative tests. We can use this to classify local extrema/relative extrema. If we know the derivative, but we don't know, if we know the derivative at a specific point, but we don't know any other information. The idea is that if f prime of a, the first derivative at x equals a equals 0, and the second derivative is greater than 0, then there is a relative minimum at x equals a, as that will be a concave up region, which corresponds to a local maxima if, local minimum if we have horizontal tangent line at that point. If we have a horizontal tangent line and the second derivative is less than 0, then there's a relative maximum because that corresponds to the peak of a concave down region. As an example, the graph of the derivative of f over the interval, closed interval 0, 8 is shown at right. We can see that the derivative is now the y value, since this is the graph of the derivative. So for increasing, decreasing, we're going to be increasing from 0 to 1 because the derivative, again on the y-axis, is positive over this interval, and between 3 and 7 because we're positive over this interval as well. We're decreasing from 1 to 3 as the sign of our derivative on the y-axis is negative, and from 7 to 8 as the sign of our derivative is negative at this point. We have a relative max at x equals 1, x equals 7 because we can see we have a critical point, our derivative is equal to 0 at these points, and our function changes from positive to negative at these points. We have a relative minimum at x equals 3 because we can see our graph changes from negative to positive, and we have a critical point where our derivative is equal to 0 briefly. We have inflection points, okay, at x equals 2 and x equals 5 because at this point, remember that the second derivative is the slope of our first derivative. The slope is horizontal and changes signs at x equals 2 and x equals 5. At x equals 0 and x equals 8, we don't have inflection points because we can't tell what's happening to, say, the left of x equals 0 or to the right of x equals 8. The mean value theorem. If a function is continuous over a closed interval AB and differentiable over the open interval AB, then there exists some point x equals c on the open interval AB such that the derivative of f at the point x equals c equals the average rate of change over the interval AB. In other words, there is a point x equals c such that the instantaneous rate of change at x equals c is equal to the average rate of change over AB. So again, if you see this problem, if you see this type of wording in a problem in the AP exam, instantaneous rate of change at x equals c is equal to average rate of change over AB, then it's asking you to set the derivative equal to the average rate of change and solve for the corresponding x value of your derivative. Okay? Note, it provided a graph of f. Check that f is differentiable first. No kinks, corners, nor vertical tangent lines. If those occur, then the mean value theorem can't be applied, and thus there's no guarantee that there's such an x value. Extreme value theorem and global extrema. If the extreme value theorem, remember, states that f is continuous over a closed interval AB, then there must be a global minimum and a global maximum over the interval. These global minimums or global maximums either occur, global minima or global maxima either occur at the endpoints or at the critical points, which constitutes the candidates test. We locate the critical points of your function over the closed interval AB. We evaluate f at the critical points and the endpoints to determine where f attains its maximum and minimum values on the interval. If the interval is unbounded, then the local extrema are automatically the global extrema. Excuse me, that is actually not correct. That's a typo. Recall that if the interval is unbounded, we take the critical points and plug them in to find their y values at the critical points. And then what we do is, instead of checking at the endpoints, we instead check for the limit as x goes to plus or minus infinity of our function in order to see how our function behaves at the as x goes to plus or minus infinity. Again, the idea being is that if our function is unbounded, the limit does not exist as x goes to plus or minus infinity, then we don't have global extrema. Whereas if we have horizontal asymptotes, we compare those horizontal asymptotes to the y values at the critical points. So this is a bit of a typo right here, so this is not automatically true. Tangent line approximations. Recalling that the derivative is represented the tangent line of, slope of the tangent line at a point on a curve. The equation for the tangent line x equals a, y equals b can be written as follows. Y minus b equals m tangent, the slope of the tangent line, times x minus a. Using this, we can approximate a function value at x equals some point near x equals a by plugging in the x value we're interested in and then just moving b to the other side, and then solving for that gives us our approximate y value at the point of interest. In order to determine the error of this approximation, recall that a tangent line will be an over slash under of over slash let me back up here. Rewind. A tangent line will over, again, I'm still messing up here, will under slash over approximate a function value if the function is concave up slash concave down at x equals a. And then the secant line will do the reverse. A secant line will under slash over approximate a function value if the function is concave down or concave up at x equals a. And again, here's how we think about that. If we have a concave up region, we draw a tangent line. We see the tangent line lies below the actual curve. So an approximation will be an actual approximation will be less than our actual function value at a concave up region. Okay, whereas a secant line will be drawn above the curve at a concave up region, so a secant line will over approximate our function value at the actual point. And that concludes day 3 of AP Calculus AB review.